In this set of lecture notes, we're going to continue our conversation about one-dimensional motion, and specifically we're going to talk about one-dimensional kinematics. Now, the term kinematics basically means study of motion without understanding the reasons for it. In other words, let's say I'm talking about throwing a ball. So let's say I throw the ball and this ball is moving through the air. Or let's just say the ball is moving. So I am going to talk about kinematics as just the movement of the ball. I am not going to consider how the ball got there. So basically I'm not going to talk about the fact that I had to throw the ball. I'm also not going to talk about what's going to happen in order to get the ball in motion. I'm also not going to talk about what would happen to the ball and how it would happen when it hits the ground. So I'm literally just going to talk about the process of motion. Now in this class, we narrow down the meaning of the word kinematics a little bit more. So the way that we're going to use it is to say that this is specifically motion with constant acceleration. So we're still not studying the reasons for this motion, not yet, but we're talking about motion with constant acceleration. So let's see if we can derive some equations here. Now, I'll remind you again that we wrote v as delta x over delta t, and we wrote a as delta v over delta t, right? So those were our definitions of velocity and acceleration. So let's start with acceleration. First thing I'm going to do is to rewrite this delta v as v final minus v initial over t final minus t initial. So that's simple enough. That's just utilizing definition of change, right? And then what I'm going to do is rearrange this equation in such a way that I'm multiplying by that t final minus t initial. So what I'm going to have is quantity t final minus t initial times acceleration equals v final minus v initial. Except that looks a little bit awkward. So let me rearrange this equation a little bit more. And I'm going to have v final minus v initial equals a times t final minus t initial. And then on top of that, I'm going to move over the v initial. So v final equals v initial plus a times t final minus t initial. So the way this equation is written, it allows us to calculate the final velocity of an object if we know initial velocity, acceleration, and the time frame over which the motion happens. Kind of looks very narrow in terms of what it allows us to do. So let's continue this and generalize it a little bit more to something that would allow us to calculate velocity at any point, not just final velocity. So I'm going to do a couple of changes here. So first of all, often we say that t initial is equal to 0. Now, it doesn't have to necessarily be the case, but typically that's how we think about motion. So with my example of throwing the ball in the air, I would have a timer, for example, in my hand, and as soon as I let go of this ball, that's when I'm going to start the timer. So that's my initial time for the process of motion. So that means that I can simplify this term and make it go to 0. Also, the other thing I'm going to do is instead of t final, I'm just going to rename it into t. Because again, I don't want to limit myself to only talking about final values or final points. I want to be able to describe every point along this motion, I want to be able to do calculations for any amount of time or any point in time during which that motion occurs. And along the same lines, I'm going to rename v final into just v, because again, my goal is to be able to describe motion at every point. So then this equation becomes v equals v initial plus a times t. Okay, I'm going to box this. So this is an equation that allows us to calculate velocity of an object whose acceleration we know. And again, this is for motion with constant acceleration only. This equation does not work for any other type of acceleration. Not that we would have to worry about that in this class. You may see this equation written as v of t equals v initial plus at. That's fine. That just emphasizes the fact that we're looking for velocity as a function of time, so we can evaluate it at any point in time. And also you may see v naught instead of v initial. So v naught or v0 represents also the initial point. So v naught and vi technically are completely equivalent terms. I like using vi a little bit more because to me that takes your mind away from having to stick with 0. So v initial could be any initial velocity that does not necessarily happen at 0. But again, those two notations are totally interchangeable. So I'm going to leave it up to you to choose which one works best for you. So for me, I use v0 when an object is at 0, and I use v initial for any other starting point throughout the process of motion. We're going to do a couple of equations, couple of problems when we get to that, so then you will see what I mean by that. So then the next equation that we need to derive has to do with definition of velocity. So let's start with that. So we have velocity equals delta x over delta t, right? So we can basically use the same exact idea here and write delta x as x final minus x initial, write delta t as t final minus t initial, okay? And kind of go about solving for x the same way. So then I'm gonna write it like this. Make the same assumptions, right? So we're gonna say that t initial is equal to 0, and instead of t final, we're gonna just write t. Instead of x final, we're just going to write x. So this is where we are so far. X final equals x initial plus v t minus t initial. That'll go to 0. And then we have x equals x initial plus v t. Now the problem with this equation is that this equation, and I'll box it too, this equation is only good for what's called uniform motion. So uniform, in this case, represents constant velocity. Although a lot of times we use the word uniform to represent not constant velocity, but constant speed. In this particular case, since we're only dealing with one-dimensional motion, it actually kind of doesn't matter. So you can almost use the words velocity and speed interchangeably here, even though they're not exactly identical. So it's a perfectly valid equation. In fact, I bet you have seen this equation before, except it probably was written this way. D equals RT. Distance equals rate times time. So distance is now, in physics, replaced with position, right, or displacement. And then, of course, instead of rate, we write velocity, because velocity is rate of change of position. So you've seen this equation before. There is absolutely nothing wrong with this equation, and it's perfectly valid, perfectly usable, except it has to deal with uniform motion. So this is not a general equation, right? General equation would allow us to account for non-uniform motion for situations where velocity is changing. So if I go back for a second and I have that equation for velocity, I can think of taking this equation and substituting it into v here. Now I'm going to wave my hands around just a little bit. I'm going to write the final version of this equation. And where I'm waving my hands and writing this 1/2. Now this equation I am going to box because this is our final version of that equation. Very useful. Now the reason I'm saying that I'm waving my hands around a little bit is because if you plug in that equation into v directly, you're actually not going to end up with that 1/2. It would be exactly the same equation minus the 1/2. So two ways of thinking about where that 1/2 is coming from. One is, if you know calculus, I'm just going to say one word and you'll recognize what it means if you know what it is. The word is integration. If you have no idea what I just said, don't worry about it, because obviously calculus is not a prerequisite for this class. So don't panic. I'm never going to ask you that. And then in that case, you can think of that 1/2 kind of sort of coming from average velocity. Not the average velocity that we defined in the previous lecture, where we were talking about instantaneous and average quantities, but average in terms of like adding initial and final, dividing that by 2, plugging everything in and simplifying. So that's kind of another way to derive this equation. Now, I actually don't want to be doing that. I don't want you to even try to derive that like on an exam or something. I want you to use these equations as is. So I'm going to write for you separately this equations just so that you have them in one spot. So 1D kinematics equations. We'll have a velocity equation. And we'll have a position equation. Now, these two equations can be used as is. You do not have to show the derivation. You can just use them in this particular method, in this particular way, in this particular form, and you never have to reinvent anything. Just use them. One more equation. I'm not going to show you the derivation of it, but I'll obviously write the equation for you. This equation here is put together by eliminating t from the other two. So basically, if you took the first of the two and solved for t in terms of v and plug it into the second equation and simplify, this is what you're going to end up with. Okay, so this equation also, you don't have to derive it, although I just told you how you would derive it. These three equations collectively is what I'm calling 1D kinematics equations. And you can solve pretty much any kinematics problem using some combination of these three equations. Now, notice that these equations are written all with x, right? Because obviously we're talking about 1D motion here. When we get to talk about 2-dimensional and 3-dimensional motion, we're basically going to apply the same three equations to other dimensions. So kind of keep that in mind somewhere in the back of your mind. Don't worry about it too much right now, but I hope you'll be able to recognize that once we get to 2 dimensions. Now, one particular kind of one-dimensional kinematics is called free fall motion. The word free fall can be written as one word, two words, or hyphenated, entirely your choice. The term free fall specifically represents motion under the influence of force of gravity only. Now, we're very much not ready to be talking about forces just yet, but I'm sure all of you guys know, or at least have a feel for what force of gravity is. You can ask any 4-year-old, and the 4-year-old will tell you what it is. You know, if you drop something, it falls to the ground because the earth is pulling on it. So that's all I'm going to say at this point in time about force of gravity. We are going to revisit that idea once we actually get to talk about forces. For now, what we need to get out of this is that when this happens, when there is only force of gravity acting on an object, as in when the earth is pulling on an object, well, earth is always pulling on everything, but in this case, for free fall, we're only saying that there is earth pulling and there is nothing else pulling or pushing this object. Basically, what that amounts to is us saying that acceleration in the y direction is equal to what I'm going to write as negative g. Two things. First of all, y direction, because typically the way that we represent something falling to the ground, right, we're going to draw that as vertical motion. Now, everything else that we've done up to now had to do with motion in the x direction. This really isn't any different. So this is one-dimensional motion in the y direction, right? So up and down movement. So that's why I'm calling it acceleration in the y direction. Okay, so I can even draw this or label this as acceleration in the y direction. Value g is a constant. We're going to use 9.80 meters per second squared. I'm going to box it. So it's not a fundamental constant, but it is a constant that we're going to be using in this class. So this little g is defined as acceleration of gravity, or due to gravity, at, on, or near the surface of the earth. So basically what that means, I'm giving this value to you as a constant, is that whenever you drop something, for example, that something is always going to accelerate towards the ground, towards, more specifically, the center of the earth at that rate. So that's a constant value for any object, independent of that object's mass, composition, size, and so on. But of course, it has to be free fall motion. So if there is other things present, other forces present besides force of gravity, this would no longer be applicable. So for the time being, when we're talking about objects falling or being thrown or being launched, unless told otherwise, you're going to assume that that's the acceleration of gravity. That's the value that you're going to be using. This value actually is derived from properties of Earth. Later down the line, we're going to see where this equation is, where this value is derived from and why it's equal to that. So we're not ready for that right now. So for now, we're just using it. Later, we will see that it depends on mass and size of Earth. So for example, if you went on a different planet, on Mars or on the moon or something like that. Yeah, I know, moon is not a planet, but whatever. So if you went into another location, this value is no longer going to be this, 9.8, right? So it's going to be something else. So this is highly dependent on location. Now, when I say at, on, or near the surface of the Earth, I don't mean near as in within a couple of centimeters of the surface. Typically, this is valid for many kilometers of the surface of the Earth. So you start seeing differences in this value kind of close to the location of the International Space Station, which is something like 300 or 400 kilometers off the surface of the Earth. Then that value changes noticeably. So we're not going to worry about that. We're not going to have to deal with objects that are that far off the surface of the Earth, at least not right now. So for all practical purposes, you're always going to use the same value for acceleration of gravity or acceleration due to gravity as long as we are on Earth. Another quick note about that is if you look at textbooks that were written kind of pre-2005-ish, somewhere there, this value is probably going to be written as 9.81 meters per second squared. So the reason for that is over the last 15 or 20 years, obviously our technology has been developing at crazy pace, and once we were able to develop our space technology and we put some more satellites out there, some more GPSs and all kinds of other stuff, right? So all of those devices were able to measure mass of Earth and size of Earth more precisely. And since this value is calculated based on properties of Earth, that's why there was somewhat of a change in the value. So it's not that the gravity itself has changed. It's the fact that our calculation has changed a little bit based on this new information, new measurements that we acquired from all of the developing technology. Okay. Now also notice that there is this extra minus sign here. Now g by itself, g is a positive constant. That's a common place for students to make an error. So g itself is positive. The only reason that I wrote ay as negative g is because it's downward towards the Earth, right? So remember, we're using our standard coordinate plane here. So we're saying that up is positive and down is negative. So I'm saying that acceleration is negative, acceleration is downward, but g itself is a positive constant. So please be careful, be mindful when using this value. So it's a constant, right? It's a value of acceleration for a specific kind of situation. But remember that these equations here, the three on top, those are general one-dimensional kinematics equations. So we can actually take those equations and adjust them a little bit to be more suitable for a free fall situation. Now, I'm not going to call those equations new equations. I'm just going to adjust this one-dimensional kinematics equations to be ready for more convenient usage. So remember, ay is negative g. So that's what I'm going to plug in. All right, so I'm going to keep all the v's and everything else and just have minus gt in the first equation. I'm also going to replace x's with y's because typically that's how we label the vertical coordinate. And again, I'm going to have minus g, right? So that term gets an extra minus sign. And then finally, in this last equation, have minus 2g and then y minus y initial. Okay. So if you want, you can box these. But again, these are not new equations. These are exactly the same one-dimensional kinematics equations with a particular value of acceleration plugged in. That's all. Let's do an example. So simpler example. We can address more complicated examples in worksheets and during office hours, but let's do a simple one. A ball is thrown straight up with initial speed of 30 meters per second. Calculate the maximum height of the ball. Okay, calculate the maximum height of the ball. Okay, so it looks like at the first glance that there isn't enough information in this problem. For example, the problem doesn't state where the ball is thrown from. So a common approach to something like this is to say that if there is no particular information given, then you can just kind of make up your own initial point. And of course, the simplest point, the simplest place where you can start from, is from the ground. So here is my ball. This ball is getting thrown up like this. And then at some point in time, it reaches maximum height. So here is my little schematic here. Remember, picture is worth 1,000 words. So it's definitely worth drawing a little quick diagram. I'm going to say that y initial is equal to 0. And y final is going to be y max. Okay, so that's the maximum height that the ball reaches. If you want, you can also label initial speed of 30 meters per second, like this. And if you want, somewhere off to the side, you can also draw acceleration, right? So this acceleration, downward obviously, acceleration due to gravity, right? We're not told about presence of any other forces or any other complications, so this is a free fall question. Now, using our knowledge of velocity and acceleration vectors, here we have velocity vector pointing up and acceleration vector is pointing down. So what is the result of having those two pointing in the opposite direction? The result is that the speed of this ball is going to be decreasing. To what point, or until when? Until it reaches the maximum height. What happens at the maximum height? The ball has to instantaneously stop and then turn around and go back. So I'm going to label it here as v final equals 0. And I'm going to say that this is instantaneously. In the future, you don't have to label it like this. You don't have to write down that this only happens instantaneously, but you do have to recognize that. This is very important. So for an instant, not a second, not any kind of time interval, but just for an instant, the ball stops and then turns around and starts going back down. So this is our turning point. How do we know that this is instantaneous? Well, because the next motion that the object is going to do, that the ball is going to do, is move downward towards the ground. Okay? So we're solving for maximum height. There is actually a couple of different approaches how you can do that. In fact, a lot of kinematics questions, one-dimensional and even two-dimensional, typically have more than one approach to them. So I'm going to show you both of those approaches just for practice. Let's start with velocity equation. And I'm going to use the free fall version because, well, that's what this problem is about, right? So those equations are all written right on top of the page right now. Why am I starting with velocity equation? Well, we know that at the final height, at the maximum height, velocity is equal to 0. So you can simplify this equation right away. We know what V initial is, and we obviously know what G is. What is this equation going to give us? A way to solve for T. So I'm going to write it like this. Okay. I solved for T algebraically. I'll talk about problem solving in a few minutes. And then we can plug in what we know. So we know initial speed of 30 meters per second. Obviously, G is positive 9.8 meters per second squared. We can plug all of that into the calculator and get 3.06 seconds. Okay, well, that's something, but it doesn't give us the final answer yet, right? We need to solve for y max. Which of the other equations, the other two, is going to give us a way to solve for y max? The y equation, right? So y is equal to y initial plus v initial t minus 1/2 gt squared. We said that y initial was 0, and we're solving for y max, right? So we have initial velocity, we already solved for time, we know what g is, so now we have enough information to plug everything in. I'm going to substitute y max instead of y, and then just plug in all these values. Notice how I'm keeping all of the units throughout these calculations. Don't forget to square that. Okay, so that can all be plugged into the calculator, and we have 45.9 meters. Okay. Another method to solve this equation, or excuse me, to solve this problem, would be to use the third equation out of the 3 kinematics equations. The problem didn't really ask for time, right? We calculated the time in order to plug it into the y equation, but we really didn't need that value other than to use it in the next calculation. So we could use the third equation. Oops. This is our third equation. We can simplify it. We can say v final is 0, y initial is 0, right? And then instead of y, I'm going to plug in y max again. So again, you can rearrange this equation algebraically. Then plug in all of the values. And hopefully come up with the same answer. Okay. So this is a simple problem. On an exam, for example, this would just be like part A of a problem or something. It would not be the entire question. It's too easy for it. Now, we're still learning, obviously. We just barely started this topic. So this would be a good problem to practice on your own before you attempt more complicated worksheet or homework problems. Another reason that I did this problem is because I wanted to demonstrate the problem-solving method to you. So let's write a couple of pointers on that. So number one, always show the equation or equations that you're using to solve the problem. So notice in this problem here, before I started plugging in numbers, I wrote all of the equations, right? Before I simplified anything, I'm always writing down the original equation. Please don't skip that step. If you do, there will be loss of points on an exam. That's supposed to say always. Number two, simplify the equation. Right? So that's where I made some of those values equal to 0, or I substituted y max into y, something like that. So I'm identifying certain values that I can simplify. Number three, solve for unknown variables algebraically. If possible. So look at what I did in all of this parts, right? I solved algebraically for t or for y max, as in I'm taking all of those values, or rather equations, and I'm rearranging everything algebraically first before I ever plug in numbers. There are a couple of reasons for that. So first reason is it shows me that you know what you're doing, that you're specifically identifying the variable that you're trying to solve for, and then you know how to solve for it. So you solve for it algebraically, and only then you say, oh, by the way, I have all of these values, I can now plug them in. The other reason for doing it like this is kind of in the long run reason. A lot of times, obviously, in your future jobs and your future careers, you're gonna possibly have to repeat various calculations. So instead of starting from scratch and plugging in these calculations or these numbers all into the same equation and then recalculating things multiple times, instead, you already have kind of a shortcut that you're plugging stuff in, right? So t is equal to vi over g. So if I give you different values for the same problem, you don't have to go back to the original equation. Now, I said whenever possible or if possible. Yeah, there are some situations in which it's inconvenient, let's say. For example, if you ever have to solve a quadratic equation, you do not have to show me quadratic equation setup. You can do as many algebraic steps as you need to. I'm not gonna take points off on that, but you don't have to. Also, we don't really need to worry about it in this class, but there are situations in which you just cannot solve for a variable. So then you plug stuff in and then have a calculator or a computer solve numerically for you. So I don't anticipate too many of those, but it's a possibility in general. So for something simple, please solve for the variable algebraically first before plugging in values. And again, you can take as many steps as you need to. I kind of skip the algebraic steps, but if you need to take several algebraic steps to rearrange equation, to, I don't know, whatever, add something, multiply something, divide something, do that. Do that in as many steps as you see necessary. Number 4, plug in all relevant numerical values with units. Okay, see how I did that? Like, for example, in this step, right? I have units in every single value that I'm identifying from what was given to us. Okay, with units. And a little aside there, when doing calculations, oops. Units follow the calculation. So let me show you what I mean by that. I'm going to take that thing that's right on top there. So I have 30 meters per second squared, and then 2 times 9.8 meters per second squared. Okay, so what do I mean units follow the calculation? Well, I'm solving for y, right? I'm expecting to get units of meters. So I'm kind of double checking my work here. I'm only going to do this with units now. So on top I would have meters squared over second squared over meters per second squared, right? So this gives me meters per second squared times second squared, excuse me, this is meters squared per second squared. See, I knew that I did something wrong, so I went right immediately back to what I missed and fixed it. That's why you need to be doing this. Okay, so seconds squared cancel out, and one of the values of meters cancel out. So doing this kind of analysis, it's sort of like dimensional analysis. This allows you to check your work while also making sure that your units are not doing something goofy. And if you get really wrong units at the end, like for example, you did all of this and you made a mistake somewhere and you got second cubed. Well, you know that height cannot be measured in second cubed. So then you know to go back and fix, you know that you've made some kind of an error in your calculation. Now, this is not a very difficult calculation, but if you ever need to like do an extra step where you drop the units and then just write this out like that and then whatever, calculate that, that is perfectly fine. You can even take a couple of extra steps, right? So for example, I can even do something like this. I mean, not that you ever need to do it, but just in case, right? You could simplify that and then plug that into your calculator. So you can do as many of those steps as you need, algebraic or arithmetic, whatever. I'm not going to be looking for that stuff. I'm looking for those important steps in problem solving. And finally, once you do all of that, you'll have your final answer with units, of course, as appropriate. Remember, there are some quantities that don't have units. Okay, but most of them do. And please box or circle or highlight or underline or star or something your answer. So basically you're setting up this problem. Doing that tells me, okay, I've solved this problem. I got the answer. This is my final result. It also makes grading significantly faster for me, but that's aside. So those steps must be present in every single problem and every single solution. Okay? You may have noticed that when I'm solving problems or when I'm writing stuff, I box important equations. And then if I'm solving problems or writing an intermediate result or something, I usually circle it. So this is how I do all of my problem solving. And then, of course, if there is an important point that I need to make in the lecture setting, then I use a highlighter to highlight whatever I'm trying to emphasize. So that's kind of my own preference. You can follow that if you'd like. But like I said, you don't have to do that. You can box your answer. That's perfectly fine. But that way you're showing me that you're done. you know you got to a certain point, and this is what it takes, and this is what the final answer is. So please make yourselves familiar with all of the steps. You can do more steps in between, algebraic or arithmetic, but these steps must be present in every single problem.